So, hello again everybody, and today what we are going to do is to basically start speaking about artificial neural networks. But first, let's go fast recap to see all of the way what we got up to here. So we started with some linear regression algorithms. Yes, the task was quite simple and clear, that we had some data points, and what we try to do is to find the best fitting approximation line, which is a linear function, and for that we used the gradient descent method. Okay. And for that we use gradient descent method to find the parameters of your line, theta 0 and theta 1, yes, and accordingly update them over iterations. So that was a linear regression with one input. Then we basically define the cost function, which is your means of verifying how good are your theta 0 and theta 1 parameters. And the gradient descent algorithm therefore was minimizing your cost function over parameter theta 0 and parameter theta 1. So perfectly speaking, we should set some initial conditions, so some starting theta 0 and theta 1, just like 0 and 0, for example, and then step by step, gradient descent solution finds the minimum converging to it. Yes, so that is the idea of linear regression. Then we have extended this beyond linear by saying, okay, if we need non-linear case, we can always produce some other terms ourselves. So like in this example, we had just one input, like x1. Then we decided, okay, I'm going to create x1 squared as another input for my model, and this way you get this non-linear behavior, in this particular case a quadratic one. But you can create other one, x power of 3, combination of x1 multiplied by x2, and so on and so on. Yes. Then we moved on to logistic regression, which is now used for predicting different kinds of classes. Yes, so this is a classification problems now, when you need to say if this data belongs to one class or to another one. Yes, and in that kind, our boundary between classes is no longer this kind of linear function we had, but rather than that, it is certain, well, we can say threshold, which separates your negative class results from positive class results. So that means your hypothesis had to be changed, and we did so by introducing the activation function, which we applied to already familiar hypothesis. So this activation function is called sigmoid activation function, or logistic activation function, which has this formula, yes, well, formula is not written here actually, but you simply have your linear regression formula and you calculate sigmoid function over that linear regression. This way, you have as output now a probability in range from 0 to 1, accordingly with 1 marking as most certain yes, and 0 marking as most certain no. And everything in between is like more like yes or no, and so on and so on. Yes, so then you have to decide based on this probability yourself what basically is this, yes or no. So again, here we can use either linear formula with first degree x1 and x2, or we can also use non-linear one like x1 square, x2 square, and so on, which then is going to produce you some non-linear behavior of this border. So it's still true as it was for linear regression. And then last time we spoke about the extending for multi-class problems when you have not just simple binary problem like yes or no, but instead you would have to decide over multiple labels, like say green triangles, blue squares, and red crosses. And for that we said there are actually quite a few algorithms that can be used. However, we are now currently going towards artificial neural networks, so logistic regression here will be our next, well, was our logical stop, but we still will discuss these algorithms as well, and we'll still try them in practical exercises too. So the idea here is quite simple, can be defined as basically one versus all approach, like divide and conquer. Yes, you simply say Okay, I don't want one classifier that is able to say if this is triangle, square, or cross, but instead I want three classifiers. Each of them is going to say is this triangle or not, is this square or not, or is this cross or not. So today we will try in practical exercise this kind of classifier too. So that means now you have to have three hypotheses, one hypothesis for each of your class, one hypothesis for blue squares, one hypothesis for green triangles, and one hypothesis for red crosses. And then you simply calculate, as a result of this hypothesis, a probability of your data point being either square, triangle, or cross, and define it as as a maximum probability among all of those three. There was an issue that you had to convert your input, yes, in some more convenient form, which is called one-hot encoding format, when you simply have basically have to have three binary hypotheses. This is the first binary hypothesis result, second binary hypothesis result, and third binary hypothesis result. Yes, and as a result, as I said, your hypothesis return a probability of belonging to this class. So, for example, the first point has 0.83 probability that this is red, 0.41 probability that this is green, yes, and 0.22 probability that this is blue. So obviously the maximum probability is for red, therefore we believe that this data point should be considered to be red. Okay? So now we can move on to neural networks, and basically we are going to extend that, but first let's try to see this problem which we had here slightly differently. So normally what we would do here is we have one hypothesis, then we train logistic regression for that hypothesis, then we have another hypothesis, train for that, and so on and so on. So normally we would create some kind of a for loop. Inside of this for loop we will repeat three hypotheses and have our answer. However, this can be actually vectorized. Yes, so nothing is really preventing you. So, like what we did normally is, so let's say here you have the hypothesis that will be green for predicting green triangle. Yes, and for this green triangle you have its own set of theta parameters. Then you have this H matrix of green triangle hypothesis. Yes. Equal as your x data multiplied by theta, yes, vector, this column. Now if you want to calculate another hypothesis, then of course you have the same data x, so the data doesn't change, the only change will be your theta vector, which is now going to be theta 2, and this one was theta 1. And finally, the last hypothesis of red crosses is going to be accordingly with theta 3. But matrix product is actually organized in such a way that you will either way have it as a result, even if you merge these three theta vectors. So this is one column, this is another column, this is another column. And normally we calculate them separately. So you have three hypotheses and you calculate them three times. But nothing is actually preventing you to get a hypothesis vector if you say you take your data x multiplied by some matrix theta, which is shown here. So in this matrix, now you have each column of the matrix as one hypothesis coefficient, and instead of calculating three hypotheses, now you have one matrix product, yes? And with this formula, you calculate all of them in one go. Yes, so this is convenient, and even more so, it will be required for us when we will speak about neural networks. And then, as a result, your hypothesis is also going to be a vector consisting of three values, right? Which is a row vector in this particular, well, basically a matrix, yes, in a sense. So where the first column of your H is going to be hypothesis result for first class, the second column hypothesis result for second class, and so on. So it is as simple as that. Now we say our theta is not a vector column, but instead multiple columns. And we change nothing at all. We still make that matrix product. Now, however, the matrix product is going to produce not one column, but also 3 columns as a result, yes? Which is all what we wanted. And the good thing about it is that the results of the first hypothesis in no way affect the results of second hypothesis. So they are here independent and can be calculated at the same time in parallel, yes, meaning that we also get actually benefit in computational speed for that. So now if we try to see this as a graphical representation, you have 3 hypotheses. Each of them is logistic regression 1, logistic regression 2, logistic regression 3, and you have the same inputs 1, x1 and xn, yes, for your each of these. So then this way you can say this is your data inputs 1, x1, x2, xe, and 3 hypotheses which you simply merge together with their inputs, so they have the same input. Yes, so this picture shows you as if we had separate 3 hypotheses with separate copies of inputs, but there is no need to actually copy your data. You can safely use your single input to all of these hypotheses. So then your structure will look somehow like this, which produces 3 hypothesis results. This is not a neural network yet, because, well, for neural network you would need the hypothesis 1 also to be depending on hypothesis 2 and hypothesis 3. Which is our next logical step, to add an extra layer at the end, yes, which will now have, so if I say this is my hypothesis 1, yes, this is hypothesis 1, this is hypothesis 2, and this is hypothesis 3. So now the result of each hypothesis is also processed, and even more so, this final layer neuron is going to consider all 3 of these hypotheses, this also and this also, and they still return the probability of green triangle, probability of blue square, and probability of red cross, yes? However, they will be different probabilities and hopefully more accurate also, because now we have considered more difficult, more non-linear logic, yes? Because of these extra connections, we achieve high non-linearity. So even if your a separate neuron function does not have any squares or third degrees, it's just a linear regression with sigmoid activation function for each neuron itself, then the combination of these different neurons is going to produce non-linear result, especially because we use activation function after each of these neurons. So this way we don't really have to worry about finding do you need squares or do you not need squares. Your neural network is either way going to produce non-linear output, and even more so, the more actual neurons you will include, the more non-linear it will become. And then these connections are having these theta parameters, like theta 1, 1, theta 1, 2, theta 1, 3, and so on. So this has all of these theta connections, and here we have extra theta. Yes, so we can say that this is described as theta matrix 1, which has the same number of columns as it has neurons here, and the same number of rows as it has neurons here. And here you will have theta 2 matrix. So now our neural network for each layer is having a set of hypotheses. So it's not just if we have 5 classes, then we have 5 hypotheses. No, now you have the same number of hypotheses as your intermediate layer, which not necessarily will be 5, it can be 1 million if you want to, why not? But the final layer is going to have your 5 or 3 or how many classes you have. So this is class 1, class 2, and class 3. Yes? So it's just that in between you can now specify as many neurons as you want. There is no strict requirement to have specifically this number of neurons for the middle layer here. It's just for the output layer. So if we put that together, so in a sense you can say that after you have calculated these logistic regressions, you do it again, yes, having one more extra layer of this, so you can say that we simply duplicate all of that stuff, all of this stuff, yes, and connect it to the end of here, so becoming as new inputs. So this then is going to be our first neural network which we consider, which has much more nonlinear behavior, yes. Now, another thing here is that we are actually this way no longer limited to having specifically a sigmoid activation function, because there are actually quite more of them, which we will also discuss today, what kinds of activation functions are there, and why some of them might be better than others, and in which cases we might want to use sigmoid, in which cases we might not want to use a sigmoid, yes? So in short, specifically, sigmoid is a very good activation function if you have a binary problem, like yes or no prediction. In other cases, there are usually better variants, yes? So here is one more neural networks which you can see here, yes. So I specifically included this from our first lecture of introduction, yes, because I wanted to show you here this theta matrix, yes. So now here all of these connections between input layer and hidden layer, so this is input layer, this is output layer, and in between we have something called a hidden layer. So in a sense we extended our logistic regression by adding this hidden layer in between, yes, because normally then we would have input and output, yes, but in this particular case now then, because of that, we are going to have three matrices, not just one. Two matrices, not just one. So here we have theta 1 matrix, which is then going to have, in this particular case, two hypotheses, hypothesis 1 and hypothesis 2. So for that, hypothesis 1 matrix, we are going to have the theta 0 equal to minus 10, minus 10, theta 1 equal to 20, and theta 2 equal to 20. That is for hypothesis 1. For hypothesis 2, our theta parameters are going to be 30, minus 20, minus 20. And together, all of that produces this theta 1 matrix. Now, here we will have theta 2. Well, normally it is also a matrix, however in this particular case we only have one output, so it's still going to be a vector. But again, this is not a strict requirement. If you can have multiple outputs, then you will have one extra column for each of these outputs. So again, minus 30, 20, and 20. So that means that you have to calculate first hypothesis for this hidden layer, middle layer, then calculate hypothesis for next layer, and as many layers as you have to now calculate over and over these hypotheses, yes? So in this particular case, this is an example of exclusive OR function, yes, which basically compares two inputs, like are they equal or not. So XOR produces 1 if the inputs do not match, so 0, 1 or 1, 0, and if the inputs are the same, then XOR produces 0, yes? And it can be represented as this kind of a neural network if you specify as x1 here, for example, 1, and x2 here, 0, then going through calculating all of these hypotheses, hidden layer 1, hidden layer 2, and output hypothesis, 3 hypotheses in total, you will get the final answer, which is correct, yes? And this separates these two classes, yes, basically in that case. However, in this neural network, you can also specify x1 and x2 as a floating numbers, yes, like 0.9 and so on. And this way you will get something like this kind of a region, which is going to be 1 and which is going to be 0. Either way, as I said, you can always add as many hidden layers as you want to. So if you have more than one hidden layer, this is called a deep neural network and deep learning as a consequence, yes? And there can be literally like even thousands of such hidden layers if we are trying to solve some very complex or very Because of that, of course, computer is going to take some time to calculate these kinds of very deep neural networks, but either way, it's completely up to you to decide how many layers do you need and how many neurons there are in one layer. So the problem itself dictates you only two factors. The first one is how many inputs do you have. So this depends completely on your data set. How many columns you have, x1, x2, x3, x4. Yes, so also do not forget that you need extra bias. So then we have x1, x2, x3, and so on. So the number of inputs depends on how many inputs your dataset has, and the number of outputs obviously on how many outputs you are having. Y2, Y3, and so on. Considering this is one hot encoding like this, yes? Because normally we have a label like saying this is a dog, this is a cat, this is a horse, this is an airplane, yes? So for that we need to convert these words, horse, dog, and so on, into this one hot encoding, which I will show how to do today in practical exercise as well. It's not very difficult. You can use actually Python's own tools to do that. But this part of neural network is completely up to you to decide. You can use either one neuron or millions of them, and it is still going to work. The accuracy of predicting, however, is going to depend a lot on your choice. So sadly, there is no certain way of knowing how many neurons do you need. It is sort of trial and error approach, which you need to repeat multiple times and pick up the best configuration of neural network you are going to have. So for that, we will have certain practical exercise too, where you will be given some data set and we'll try different neural networks and then decide whichever is better. But before that, we actually need to solve one big problem. Well, first of all, the first problem is two problems, yes? One is small problem and one is huge problem, yes? So the small problem is that you are going to need to somehow program this stuff, yes? But we already know kind of how to do this because you need to calculate hypothesis, all hypotheses for each layer, which is a matrix product. Then you need to calculate hypothesis for next layer, again matrix product, and for the last layer, again matrix product. So in a sense, you need to calculate as many matrix products, as many layers your neural network has. This is a small problem because we already know how to do that. Yes, we did that for one hypothesis, but we can extend it for multiple hypotheses, no problem. Another issue is how many neurons do you need? Yes, so for example, here you can see the configuration of neural network, this first one. So we have only one hidden layer, and we change how many neurons do you have in that hidden layer. And here you can see that at the first picture we only have 3 neurons, and your basically boundary between two classes, this limit, yes, is somewhat generic, you can say. Yes, it is non-linear function still, but it's nothing too complex. As you can see, it produces some errors because here we have red point in green area, here we have green point in red area, so it's not over accurately. Then we want to improve the accuracy by adding more neurons. So now instead of 3 neurons, you are going to add 3 more neurons, then again repeat the training procedure, for example using gradient search method, and you will see that now this boundary becomes more complicated shape. If you continue to increase the number of neurons, then you actually get, well, again, overfitting problem, yes, because this is clearly too tailored for this specific data set and may not necessarily work well with some new unfamiliar data. So we have here overfitting problem because you added too much of these neurons. So in a sense, this is also a good news for us because this way we can actually do regularization without adding this lambda parameter, but simply specifying how many neurons do you have. And controlling this number of neurons is also your way of regularizing the system, yes? So in a sense, for neural network, there are multiple ways to do this regularization. Of course, as before, you can still include lambda parameter and the calculating all theta parameters in that as well. Yes, so let's say you have, I don't know how many, let's say 20 neurons, yes, 20 hidden neurons, and you still want to use 20 neurons, yes, but because of that you are going to have to get back to that lambda parameter, introduce it, and it is still possible to regularize that even for 20 neurons, yes, so now you have two ways of regularizing neural networks, and there are actually two types of regularization, L1 regularization and L2 regularization, which in a sense is a very simple thing, yes, nothing too complex. For L2 regularization you have a summation of theta parameters squared, which we discussed, and for L1 regularization you have them without square but absolute values, yes, so no square for L1 and square for L2. So according to that's where it stands, this 1 or this 2 as a power of this summation, yes? So that is quite simple. Now another huge problem for us, which is going to probably even take us not one but two practical exercise times, is how to train this neural network, how this training is actually happening, because now we have this kind of a complex structure. So in this example, our neural network tries to recognize handwritten digits like 5 as 5, 4 as 4, and so on. And therefore, you can see here 10 possible outputs for each of the possible digits, starting from 0, yes, starting here, all the way up to 9. And normally trained neural network should show as a maximum probability only one of these numbers. So, for example, in this particular case, we can see that this neural network is going to decide that this picture shows number 4, because this is, well, if we consider this as some kind of LED indicators, this is light up the most compared to others, yes? So others are somewhat dimmed, and this is the brightest one. Well, which of course is not the correct answer in this particular case, so that neural network needs training. So how does this training actually happens for this neural network? We know that for a single neuron, we are calculating some cost function, and then using this cost function and derivative of this cost function for each of these inputs, we update theta parameter. However, here you can see a lot of those connections, so that means you are going to have a huge amount of these derivatives, but nonetheless it still works more or less the same. It's just, you know, not quality but quantity of the calculations that are necessary to be filled in. So in a sense, if we try to visualize this learning process for the neural network, this is actually how these theta parameters are updated, yes, by using the kind of equations. Don't worry if they look scary now, but we'll get to the bottom of this next time, and we will actually even, code them ourselves. So we will write our own program that trains neural network with everything that we use ourselves. What I wanted to mention here specifically, however, is one thing, that here you can see that you are going to use something called a sigmoid derivative. So we no longer calculate derivative for the cost function, but we calculate derivative for our activator function. And this is specifically much more simple, because you can choose your activation function so that it will be easier for you to calculate derivative. And for the cost function, well, you literally don't really have their other choice other than this derivative. But either way, we'll return to these formulas next time, yes. What I wanted to show is how this training.
But once you unwrap what each part of this algorithm is really doing, each individual effect that it's having is actually pretty intuitive.
Once you have this output, so in this particular case, it's saying that this is shown as 0, which is not true, yes, because this is the brightest point here, 0. It shows that the probability for it to be 0 is the highest. So now this is incorrect answer. At the same time, of course, we know the correct answers in a one-hot encoding way. So this should be 0, this should be 0, this should be 1, and all the others should be zeros, yes? So accordingly, the correct answer would be here. This is returned as a probabilities, which you can then calculate difference between 1 and this probability, 0 and this probability, and have therefore your cost function. Now this cost function is then going to be split into small fractions of errors, which are going to update each of these connections you are having here, and they are going to go backwards. Yes, so basically what happens now, you can see that our
It's just that there's a lot of little adjustments getting layered on top of each other.
calculate error and the error back propagate.
So I'm going to start things off here with a complete disregard for the notation and just step through those examples. The way that we adjust the weights and biases for a single is having a certain cost per example over all the tens of thousands of training examples. The way that we adjust the weights and biases for a single gradient descent step also depends on every single example. Or rather, in principle it should, but for computational efficiency, we're going to do a little trick later to keep you from needing to hit every single example for every single step.
Whichever is better.
In either case, right now,
So again, we will speak about actually training neural networks a little bit further, because this is quite complex, and we are also going to need to be able to program it ourselves. But at this point, let's go further and see how other activation functions can be used and why we might want to use other activation functions. So we know this particular activation function called the sigmoid, which compresses your range from minus infinity to plus infinity all the way to the range of 0 to 1. And here you can see these logistic functions, so-called cumulative distribution functions. So this is actually a distribution in probability theory, just like any other, and this is a cumulative distribution function. Yes. Now, so where was that? It will be further. Okay. It will be further. Let me get this point. Now, when we will actually run training of this neural network, you are going to need to calculate the derivative of this activation function. Yes, so here you can see, for example, derivative of sigmoid, derivative of the sigmoid. And well, with one of the groups yesterday we had our practical exercise, and I told you that actually this cumulative distribution function, called CDF for short, yes, CDF, is an integral of the probability density function, which means in return that derivative of the CDF over some x, yes, is going to be probability density function, meaning that this should look like somehow like this kind of a function, yes, which it indeed does. But again, it's not exactly a normal distribution, it's actually its own distribution called a logistic distribution, yes. So here you can see in the red color this derivative of the sigmoid, yes. Now this derivative is quite small, as you can see from here, which is not convenient, especially if you have a lot of neurons, and that is going to mean that your finding for solution might become slow because this derivative is just too small, yes. So we may want to try to increase it. One way of doing that is to replace your sigmoid activation function with a hyperbolic tangent activation function. The difference here between sigmoid and hyperbolic tangent is now that sigmoid was capping at 0, whereas hyperbolic tangent is now capping at -1, all the way up to +1. And sigmoid was going in the middle point of 0. Well, I don't have it shown well, but somehow like this, was capping through point 0.5, while as tangent function is going directly through 0 at 0. Now the derivative of hyperbolic tangent is much larger. It also looks similar to the normal distribution. In fact, many of them will look similar because this is just how the function of cumulative distribution looks in general. Yes, we can shift it, we can compress it, stretch it, but its S-type shape, yes, is going to be, well, all over there. So for this kind, we can actually use hyperbolic tangent activation function, but here you need to realize that now your outputs are going to be both positives and negatives, yes? So this is something to keep mind about. Another way of using another kind of activation function when we do not really want to have the negative numbers is called rectified linear unit. So this activation function does not convert your output in the range to -1 to +1. Even more so, if your input is positive, then it changes nothing, so it can actually be big numbers if necessary. So for positive numbers nothing changes, but if the number is negative, it's just going to replace any negative number with a 0. So as simple as that. And this is actually non-linear operation, because you cannot achieve that by adding or subtracting some numbers, this kind of effect, yes? And the derivative of this kind of a function is also quite simple, yes? So the derivative of this 0 is 0, and the derivative of this line is 1. And here at 0 you have this singularity point, this jump, yes, when your derivative suddenly becomes from 0, 1. And in this sense you have very convenient and nice derivative function. It's actually not even a function, it's more like a 0 or 1, yes, depending if your number is positive, then it is 1, if your number is negative, then it is 0. So in a sense you simply take the sign as the derivative and that's it. A very simple and easy to calculate derivative, and also very fast, yes, so now your derivative is being calculated very fast, which is again a benefit if you have millions of these neurons, and for each neuron connection, it's not just neuron, but each neuron connection of these million neurons with other neurons, you are going to need to calculate this derivative. Then having it as simple as to 0 or 1 is very, very good for us being to be able to calculate it fast. Yes. Now another activation function which we normally use. So if we use ReLU, hyperbolic tangent, sigmoid activation functions basically for any of these layers, then specifically speaking about the output layer only, sometimes we use a softmax function. So this is activation function normally used only for output neurons, not the hidden layer neurons or any other neurons. Why is it necessary? So let's compare how our problem of classifying some multi-class problem would work if you have output neurons of the sigmoid activation function or output neurons of the softmax activation function. So let's start from sigmoid. For sigmoid, all of these probabilities are not depending on each other. So because of that, it's going to predict them separately. So this is a probability of class 1. This is probability of class 2. This is probability of class 3. And this is probability of class 4. And in general, the total, adding total together all of this number, may not necessarily be strictly 1, because this is not a set of full events, how they speak in probability. These are rather separate, independent estimates which in no way relate to each other at all. Yes? So because of that, we have some kind of a problem here. Yes, we can obviously say that this is probably class 2, but how confident can we be about that if class 1, for example, has also quite high probability of 0.88, or class 3, 0.76. So the difference between class 1 and class 2 is not so huge, and it still leaves us some kind of doubt if we are actually correct saying that this is class 2, because class 1 also has high probability of this. It's just that class 2 is bigger probability, and therefore we believe that it is true. With softmax, it's actually easier to decide, because now we have much higher difference. Your class 1 is 0.87, and class 2, and class 1 is 0.08. And here we have no doubts at all that this is indeed class 2. Yes, and even more so, adding all of these probabilities together is going to produce 1 in total. So now this is a full set of events with a total probability of 1. And softmax, in this sense, for multi-class problems is therefore preferred. And it's quite common thing to have this kind of configuration for neural network, having ReLU for hidden layer and softmax for output layer. Sigmoid is still not like forgotten or not really used. It's very commonly used for the binary problems where you have yes or no options only. But other than that, it really works just better having the softmax and ReLU combined together. Yes. So this is one of the reasons why we want them. And softmax also has its own function. Yes, as you can see here. However, pay attention that although it seems to be very similar to sigmoid function, it actually is really similar. Yes, there is one slight difference here, that the sigmoid goes through the point 0.5 at 0, whereas softmax does not. Yes, so this is their difference, and it's still exponential. Yes, function as well. So that is the difference between the softmax and the sigmoid activated functions. Next, another important step which we are going to use further, because at certain point when we will learn how to create our neural network, how to train it, we are going to stop writing our own code and start using some existing Python libraries, which means we will need to understand what kind of optimization procedures we can use. And the gradient descent optimization procedure which we have been used can be slightly customized. So let's see what kind of gradient descent we can use. So normally how we were using it was like we go through all of our data that we have. So we take all our entire data set, then we calculate cost, and from this cost we then do update theta j, like theta j minus alpha multiplied by derivative of cost versus theta j. We do so only after we have scanned the full data set from the beginning to the end. Now there is an alternative for that, which may or may not, depending on your data set, depending on your particular choice, actually make it faster for you to train this, so requiring less iterations. What if we say now that we do not take the entire data set, but instead we take a small part of this data set, calculate cost function for that, and then do update before we have actually gone through this entire data set. So the next data set, so now you have update, and then you take the next part of the data set, you calculate the cost again, and you do update again. So this is called mini batch gradient descent algorithm, and it allows you to do multiple updates per one go of dataset, allowing you to converge the solution faster. You will no longer need 100 of iterations, maybe you will have enough like 10 iterations to find a solution, which of course still has more computations, but this can also affect accuracy. So this is one of the ways to actually have this batch and process data in small batches, because sometimes your dataset might be just too big. Yes, you might have like billions of your records, and if you use normal gradient descent we have been using, you cannot really advance further until you have gone through all of this data, which may not be completely necessary. Here, however, you can split into fractions and update it much faster, not necessarily having to wait for all of it. It's just like I showed you in this video, yes?
Gradient descent step also depends on every single a certain involves because the cost function. But once you want what each part of this algorithm is really doing, each individual effect that it's having is actually pretty intuitive. It's just that there's a lot of little adjustments getting layered on top of each other. So I'm gonna start things out. Right now, all we're gonna do is focus our attention on one single trick later to keep you from needing to hit every single example for every single step. In either case, right now, all we're gonna do is we can't. Network is not well trained to get adjusted on how the weights and biases get adjusted. Let's say we're at a point where the network is not well trained yet. So the activations in the output are gonna look pretty random. Maybe.
But this is actually one of the ways. And in that case, your cost function, depending on the number of iterations, might actually become no longer this smooth line, but more like this varying line. But its total trend is still going to be the same as it was before. So if we see the total pattern of this line, it is more or less the same. It's just that it is not so stable anymore and can require you to have somewhat more of these runs to find out. Now there is also another variation of gradient descent which we are going to use quite actively further. Is called stochastic gradient descent, or for short SGD. Yes? And it is different in a sense that you take the small batch, but you create this batch not consequentially like it was here. Yes, you start from here, then you go here, then you go here, here, and so on. But instead of that, you jump randomly in your data set. So let's say from the beginning you take here some batch, then next batch is going to be from here, next batch is going to be from here, next batch is going to be here, and so forth and so forth. Yes, so your batch is actually randomly picked up from this data set. It can be one entry or multiple entries. Actually, this is a parameter. You will be able to specify what is the size of the batch you want to use. But the idea is that it simply tries to pick up the data randomly. Well, because sometimes, often, our data set may be organized in such a way. For example, this data set of handwritten digits we are going to use here, yes, is organized in such a way that first we have all the data for zeros, then all the data for ones, then all the data for twos, and so on and so on. So it is actually quite a good idea to mix up this data before actually using it, so that in your batch you will have, well, different numbers, not like you will have batch of 10 data points and all of them are zeros. Yes, this is not so good for our neural network. It would be much better if in your batch you would actually have all different numbers possible. Yes, but it is not always possible with the data sets we have. So we have to randomize this a little bit ourselves to make sure that our data varies as much as it can. So next then, let's speak how we are going to program our neural network. Because, well, this is going to be your task, one of the practical exercise tasks. And obviously, before you can actually train a neural network, that is, update its weights, you are needing first to calculate its prediction. Yes, so that's how a neural network is trained. First, you predict something, then you calculate how your prediction is different from what is actual answer, calculate error of this prediction, and this error is then back-propagated all the way to the beginning, in the process updating all the connections between neurons. So that's how we do it. So because of that, the first step even during the training neural network, is to actually run this neural network, yes? So, which we'll discuss now, how to run this. And basically, if you want to, you can try, yes, after today's practical exercise, you will be able to program this neural network yourself. It's just that you are going to need some neural network, which we currently do not have, yes? So let's make some notations here. Let's say that your inputs of each layer, yes, so like here, or like here, or accordingly here, are going to be denoted by a small letter A. So this is A of the first layer, this is A of the second layer, and this is A of the third layer. So these are inputs, and inputs should include also a bias. So now you need to add this bias for every layer you have. So we introduce it in our data set, then you introduce it into the hidden layer, and for the output layer we do not need bias because it doesn't go any further, it stops it here, yes? But if we were to have, like here, 4 layers, then you would need to have bias here, so here you have to add bias, here you have to add bias, and here you have to add bias. So this is operation that you are required to do. The bias is not going to be provided for you automatically. That is something we need to do ourselves. And for each layer, this bias has to be added again. So as I said then, we have our input, A, without bias. So actually I was drawing it incorrectly. Our A is here. Our A2 is here. And this is our A3 because it doesn't have bias. So then we add to this input a bias, extra column of 1s, and calculate the activation function. Not just activation function, but this hypothesis. Yes, hypothesis of activation function of the theta multiplied by, well, let's say like this. Z is equal to theta multiplied by, so Z. Here it is actually written, yes, here it is. So Z second is going to be calculated as theta of the first layer and A of the first layer with a bias, yes? And then you calculate A second as the sigmoid of Z second. Yes, so it says here, actually, yes. So this is no different than any normal matrix multiplication. So you take your theta matrix, you take your inputs matrix, multiply them over together by running numpy dot, for example, and get the matrix as an answer. Then you calculate sigmoid for each element of this matrix, and again, then you take this result, A2, to multiply with the next layer's matrix here. Yes, so this also is described by theta2, all of these connections, yes? Then you take A2, multiply by this theta2, get this Z3, for which you calculate sigmoid, and that is your final hypothesis for this neural network. So there are basically 3 steps here, yes? At the input we add column of 1s, then we calculate this hypothesis with this column of 1s, calculate activation function, then we use this result as the input for the next layer, again calculate this hypothesis, calculate the activation function, and get the result. So this can actually be even automated if you happen to have a lot of layers and don't want to write specifically for each of these, yes? Then you can try to do some for loop and go through different matrices. But in that kind of event, you would probably have theta as 3-dimensional array. Probably this way it would be easier to actually get readings for certain planes, certain, like, 3D arrays from this. Like, it can be displayed, I don't know, like this is theta 1 matrix, yes, which consists of rows and columns. Then you have on top of that extra sheet theta 2, then you have theta 3, and so on and so on. So in total, this is a three-dimensional structure, like a stack of sheets, and each sheet of them is a separate matrix having rows and columns, yes? So the idea can be like that. Then our final hypothesis can be then recursively written like this, yes? So you take your input x, add a column of ones, multiply with theta 1, calculate sigmoid in this particular case, or maybe not a sigmoid, maybe a ReLU. Any activation function can be actually used. Then you multiply this result, then you add a column of ones, multiply this result with theta 2, again calculate activation, and there you have it. So if you would have extra layer, then you would need to repeat this procedure again. Extra bias, multiply with theta matrix, activation function, yes? So for each layer, these are three steps you need to do. Yes, multiplication, activation, add bias. As simple as that. And how many layers you have, that is how many times you have to reproduce this. So for example, this neural network having 4 layers, yes, has 3 such multiplications. You have theta 1 matrix, which describes these first connections, theta 2 matrix describing these connections, and theta 3 matrix describing these connections, yes. And according to the first input is your data set, which you have, you add a +1 bias for it. Then you calculate this matrix product, apply your activation function, add bias for the next layer, calculate matrix product, apply activation, add bias for the next layer, calculate matrix product, apply activation, and there you have it, yes? So, quite repetitive tasks. And each of these matrix product calculation is none other than multi-class logistic regression, which we already know. It's just that you have to repeat it over and over again for each layer. So in a sense, all of this comes together, and we can clearly see now that how from the simplest linear regression we get all the way up to complex neural networks. This is kind of neural network we are going to use. Now, the training procedure is, as I said, quite difficult to explain, especially if we try to derive some formulas for that, which I'm not sure we are going to do, but at least I will give it a try to show you that. But if we try to put it simply in some kind of list of tasks that are necessary to do to train a neural network, then the backpropagation algorithm works as follows. First, we calculate the error of prediction. So your neurons have certain probabilities like 0.1, 0.3, 0.75 maybe, yes, and you have correct answers, like here we have 1, here we have 0, 0, 0, yes? So then you can calculate the error for this neuron as the difference squared, 1 minus 0.75 squared, and then this error can be split into fractions, yes? That is how it is done, because this error comes actually from all of these neurons having theta 0, theta 1, theta 2, and theta 3. And what we do not know is how much of this error comes from theta 0, how much of this error comes from theta 1, how much of it comes from theta 2, and so on. So to do that, we need to calculate some derivatives, just like we did in the gradient descent method. But here, however, it is a little bit simpler, because some of the majority of the math has been already done for you, and we will be left with calculating derivative of the activation function, because this can change, yes? Sometimes you use sigmoid, sometimes you use hyperproduct tangent, sometimes you use rectified linear units, yes? Which again is depending on your choice of activation functions. Then we repeat the same procedure for the second neuron, for the third neuron, and this way we go all the way up to here. Then again you calculate error for this neuron and backpropagate it even further. For this neuron, backpropagate it even further. So you can see that basically your error here goes all the way up to some input. Yes, then all the way for the second input and third input and so on. So the number of these paths is huge, yes, especially if you have multiple layers or a lot of hidden layer neurons. But nonetheless, the operation itself is calculated for each of these paths. Is exactly the same, so it can be vectorized in matrix form as well. And the solution would look like, well, first of all, let me remark one important thing. How is your cost function going to become different? In a sense, it is very similar as to what was for logistic regression, with only one small change, that in this logistic regression, your theta was a vector. And in this case, your theta now is a matrix. Yes? Because of that, we need to go over not only one dimension like here, we had one column and that is it, but over each column and each row. So because of that, we calculate here this summation twice, over the rows and over the columns. Yes? Other than that, there is no huge difference. You still take your real output y, you still take logarithm of your hypothesis, 1 minus real answer, 1 minus real answer, logarithm of hypothesis here, and also the regularization part. Yes. However, in the regularization part, yes, you will actually have also to consider layers. So you calculate regularization for all of the layers at once. So this is for theta, I believe, row. This is for theta column. And this is for layers, because you have multiple layers and multiple thetas, theta 1, theta 2, theta 3, matrix. Yes, here you only have one column, so you simply add all of these numbers together and have one column-wise summation. And that is it. There is only one neuron here, no layers, no whatsoever. So because of that, here is one summation, here is three summation. Column, row, and layers. Yes. Here we go through only through columns and rows for each of them, because each of them needs to be calculated separately. Other than that, this cost function is, well, literally is the same, yes, literally. If we use the sigmoid activation function, actually, that is important to remark, yes? Because for other activation functions, this might be somewhat different. Now, if we try to write down this algorithm of training neural network, then it looks like this. You have the first input, x, your data set, with a bias column of ones. Then you calculate multiplication with theta 1, apply activation function, calculate add column of ones, calculate this matrix multiplication, apply activation, add column of ones, and again. So quite simple and straightforward to get the predictions. Yes. So then after this step, you will have hypothesis predictions, which may be true, maybe not. Yes. But at any rate, you will be able to calculate the error of these predictions, called delta. Yes. So here at this output, we are going to have delta 4, which is calculated as simply as comparing what is your prediction and what is the real answer, which is the difference, as simple as that. Now we are going to backpropagate this error in the last layer into error in the third layer by using this formula. So some mathematical outputs I will try my best to explain next time, but it is quite complex either way. But the idea is quite simple. For that, you need to know the previous layer's error. You need to know your connection, so theta 3 describes all of these connections between these two layers, yes? And you need to know the derivative of activation function. Yes? So, for example, derivative of the sigmoid function or any other. And at this step, then this procedure is going to iteratively repeat until you get back to the beginning and find out all of these errors. So this is going to be a vector. Well, actually even matrix, I believe, yes? Because, for example, for this neuron, you are going to find what is the error from this path, what is the error from this path, from this path, from this path, from this path, and so on, yes? Then for each of these neurons, you find this particular error which comes specifically over this path, yes? So you split your error into components, yes, from each connection of this neuron. So, as I said, quite complicated way to get these formulas, but the idea is formulas is quite simple. You quite use the previous layer's error to update the other error, to update it here, and each of these errors shows you how you need to change plus minus theta 1, theta plus minus theta 1, plus minus theta 2, etc., etc. So in a sense, this is our derivative which we were using previously, like so, yes, alpha multiplied by a derivative of your cost, yes, where's theta j. So in a sense now, instead of that, we put our delta, yes? And if you know calculus, then you know that actually derivative is this delta when delta t approaches 0. So this is in a sense a limit of the difference, yes? It's just this difference is in between very small points. So at this point we say specifically, well, we don't really care about it being actual derivative. Well, let it be approximate estimate of derivative, but something we can easily calculate. And this also becomes clear why we cared so much about different kinds of activation functions, because here you need to calculate derivative of that activation functions. And if we return back, here, for example, you can clearly see that the ReLU derivative is a champion here, because it is very simple. If number is negative, it's 0. If number is positive, it's 1. Otherwise, basically, yes, we can say that you are going to need to have this function as a mathematical expression, which you can then input, which is not difficult. You can actually take this, let's say, sigmoid function, calculate derivative of it, and then use that as expression, yes? Or if you use this one, for example, again, you need to calculate some calculus, express this derivative, and put that in that formula. So this is our, so in a sense, let's say g of z derivative, and this is our g of z. So that means you are going to take this and calculate its derivative over x and get this formula, yes? And for ReLU, you don't really need to do that. It's simply as saying what is the sign of this number, plus or minus. If it is minus, then it's 0. If it's plus, then it's 1. And that is very simple. That's why this ReLU is actually very commonly used, because this also, you need to realize that this will be calculated for each of these connections. Yes, each of these connections you can see here is going to need to calculate this derivative for this layer, for this layer, for this layer. Yes, and because of that, well, we want, well, generally speaking, calculating some derivative is quite time-consuming operation. We want to be as simple as possible. And okay, to finalize today's lecture, let's also see what kinds of neural networks are there, because this is a plain, regular neural network, artificial neural network, which we have discussed, but there are actually quite more different variations of these neural networks. So you can see some of them, not everything possible, yes, listed here. And we discussed something called multi-layered perceptron, yes? So this is basically structure having multiple layers, as it states, yes? Now, if you have a lot of these hidden layers, then this is considered something called deep neural networks. In deep neural networks, we usually have like even hundreds of these hidden layers. So this is quite complicated structure, and it is believed to be inspired, yes, by our own brain constructor, because in our brain, neurons can have such deep connections, like even hundreds and thousands of layers, yes? Another type of neural network is called convolutional neural networks, which is focused on image processing, recurrent neural networks, radial basis function neural networks, modular neural networks, generative autoencoders, restricted Boltzmann machines, and so on. So let's go through some of them quite fast to understand basic idea how they work. So in deep neural network, basically if it has more than one hidden layer, we can already say that this can be considered as a deep neural network. The convolutional neural network still includes this part which we have discussed, so this is our neural network we have discussed all the way up till now, but it has certain special layers. So in normal neural networks we have all of these layers the same, yes, this is the same, this is the same. In convolutional neural networks there are different other types of layers. So for example here you can see something called a flattening layer, or a pooling layer, or convolutional layer, yes? And this convolutional layer calculates some, well, you can think of this convolutional layer as some sort of a filter. The idea is quite simple. You probably know this kind of programs like Photoshop and similar, when you can load some image, then can do some, I don't know, blurring, maybe sharpening, maybe change correction, change colors and all that stuff. And all of that is achieved by calculating these convolutional filters inside this Photoshop program. Actually, there is some math behind that. Even more so, if you are interested, you can always try to experiment with that by following this link and specifying it. So let's try it maybe. Yes, it's easy to do. So we have some picture here, which we can somehow modify. Yes, for example, this is the convolutional filter applied to this picture, which makes it sharpened. I can try another, let's say blurring it. Now you can see that this matrix changed and the picture became blurry, yes, because, well, what it does, in a sense, speaking very easily, yes, just maybe a few words, yes, is that it takes 9 pixels, so, for example, this part of pictures, consisting of 9 pixels, takes central pixels and makes it average of all of these 9 pixels, yes, and others are accordingly even smaller. So basically it replaces each pixel with the average of its surrounding pixel. Because of that, this picture becomes blurry. Whereas the sharpen does the quite opposite, yes? The sharpen actually amplifies the central pixel and reduces the effect of neighboring pixels. There is also another kind of processing you can use to be able to maybe, like, you know, hide, to make some details of this image easier to see, yes? So these different filters. However, in convolutional neural networks, the idea is that we don't really know what is this matrix, yes? So, like, what kind of numbers do you need to have, for example, to identify a dog in a picture, which we don't know? And that is exactly this equivalent of the theta parameters we are using in this kind. So these are unknown numbers which you find through optimization procedure for convolutional layers. And there is multiple such kinds of convolutional filters which you apply towards the picture. Yes? So basically, after this, you will have, well, your pictures are normally quite big, yes? You have, I don't know, like million pixel by million pixels, that is a lot of pixels, and this kind of neural network then will be very difficult to calculate that large data just for one picture, and you will have a lot of these pictures, yes, like thousands of such pictures. So what is happening here is your billions of pixels are now converted into much smaller number of most important features, which are then easily are handled by our regular neural network. That is the main idea, yes? And that's why it's used for pictures. So here we can see some more explanation, like also pictures are usually two-dimensional, yes, they have x and y axis, and this neural networks only expects you to have one column, Yes. So this flattening layer does this conversion for you. It converts your matrix into one long vector, which is then easily handled by normal, traditional neural network. Another type of neural network is called recurrent neural network, yes, which is different from classical neural networks in the sense that now it has this input state, yes, its own internal state, and also it is possible for this neural network to work in both directions. So, for example, here you can see some translation of English phrase into German and French, as I believe, yes? And it's not as simple as to take one word and then take vocabulary, replace that word, and keep the same order as it was in English. Obviously, in German, the order of words is different, in French, order of words is different, so the order also matters. That's where here comes our convolutional neural network, yes? So here we have the input. So let's say, for example, this word has, yes? And then we calculate not one hypothesis, but two hypotheses, yes? So this is, well, in a sense we can say past. So everything that was all the way up to before this word, and this, in a sense, is a future. Like what is after. So that means that data in your neural networks actually flows in both directions, not just like in a regular network from input to the output, but also at the same time, not during a training process, but normal operation mode in both directions, because you need to work with this word has relatively to other words which are before your word has and after this word has. So it is a bidirectional neural network, which is very good when working with some words, with some texts, automated translations, and so forth. Well, also in a sense, ChatGPT is in a certain way related to this recurrent neural network, but instead it is using something called transformer networks, yes, which is somewhat different. Now, this is a radial basis function neural networks, which has slightly different approach of calculating these activation functions, yes, but otherwise it is similar to regular neural networks, except that there are different types of neurons. Yes, here you can see some kind of M neurons, H neurons, but you can, if you are interested, follow this link or watch this short video to get more modular neural networks when you actually have not one neural network but different neural networks. Well, again, it's very simple as we started, yes, like at the beginning when we said here we want to have different classifiers for different cases. Now, however, we operate not in a sense of logistic regression, but okay, I'm going to make a different neural network for this, different neural network for this, and different neural network for this. So in total, 3 different neural networks, which I can actually then combine together into a modular network, yes, like here. And each part of this neural network is going to be specialized in a certain, its own task, yes. So this is one other way of neural networks. Another interesting approach is something called generative adversarial network. So this is quite commonly used to actually generate some data. So like, let's say, I don't know, you want to try find in internet some pictures of artificially generated grass, for example, yes? Or maybe some person face which doesn't really exist in the world, yes, which was generated by artificial neural networks. So that is the task for generative adversarial networks, GAN for short. So it has some existing pictures, so let's say photos of everybody here, yes, as a base to learn. Then it takes some noise and generates some new fake image of some person who is not here and maybe not even exist in the world at all, based on the proportions of face, the colors, you know, and all that stuff. And then we can actually even use this neural network to identify whether this was real picture or it was a fake one, yes, a generated one. So this is in fact quite good tool when you are considering that you need to actually verify some, well, I don't know, some pictures or some maybe even videos, if this is fake video or not, if this was created by using artificial neural networks or not. So in this sense, this kind of networks can actually help you with that. Another important thing here is something called autoencoders. Now this is close to transformers, which is basically what ChatGPT is working, but autoencoders, well, basically replaces some, well, you can think of it as some kind of encoding indeed, like you have normal letters here, A, B, C, D, E, and then let's say here you want to use some secret symbols to create your own alphabet, I don't know, some numbers, for example, like A is going to be 1, B is going to be 2, C is going to be 3, or any random number combination. So this way you can actually do this encoding and decoding for you by using this kind of artificial neural network. Normally we specify training data set and training answers. However, here you can see that we specify both inputs the same. And in a sense, this is a neural network consisting of two neural networks. So this is the first part, X train. And this is the second part. So in between here you have these predictions Y train, but this Y train is reversely again converted into X train. So in a sense this again works about generating some more artificial data. So let's say you have some data set which only has 100 entries and you want to have, I don't know, let's say 1 million of them instead. And you cannot get more data anyway otherwise, yes? So you can try to use the data you have to generate some fresh, simulate some similar data to extend this data set, yes? That is the idea of this encoding. And there is also one more neural network called restricted Boltzmann machine, which is, well, I don't really want to get deep into much theory now, because also we should be finishing by now, but I believe these neural networks was quite special in the way that they not necessarily have all the possible connections, yes? Because normal neural networks have connected every neurons with each other, but restricted Boltzmann machine can actually have some connections missing. Yeah? So there are certain allowed and disallowed connections. Like for example, you can actually try to connect even these neurons together, which is not something you do in regular neural networks, yes? But it's something that can be done in, for example, restricted Boltzmann machines. And yes, that is basically it. Here you can see some difference between what is autoencoders and what is generative neural networks. Yes, they seem to be doing same stuff, generating new data, but they work quite different. Again, we will speak of this a little bit more during upcoming lectures. This is just some review to show you that there is actually much more to neural networks than what we have learned today. But the basis for all of that is a simple, plain, regular network, which we will try to do already in 2 weeks, yes, in our practical exercise. We will try to train it as well. So that is it for today's lecture. Thank you for attention, and then, as I remind you, next week we do not have any classes, yes, just follow the Ortus information, and we will meet again with one of groups on Tuesday and with all of you on Wednesday in 2 weeks, yes. And another group that has practical exercise today, it has practical exercise. Okay, thank you.